Okay, so welcome once again, everyone. Tonight we're going to be talking about understanding two-body orbits. Think of it as when one thing that's small is orbiting one thing that's large. That's essentially it. There are all kinds of other multiple body orbits that we won't get into because those are the realm of supercomputers. So we'll do that. But as usual, first we'll start with the news. So the James Webb Space Telescope, aka the Webb, has settled into its orbit near the Sun-Earth L2 Lagrangian point. And so there's a lot of what does that mean and what does it look like and those sorts of things. So I went to my source, which is the Space Telescope Science Institute, their site, because I have access to that. And there's actually, when it says JWST user documentation, they're not talking about the general public. They're talking about if you're a professional astronomer and you want to be the principal scientist of some research project, you need to learn how the telescope works. So there's a whole bunch of documentation you can access, and they refer to it as user documentation because you're a user of the instrument. And so one of the sections they have is the characteristics of the James Webb Space Telescope, including its orbit. And then why is it at this weird orbit? But best of all is this picture, which is a three-dimensional picture. You have x-axis, y-axis, and z-axis. And on the left, you have, it says Earth, but this circle is not the Earth. The dot in the center of the circle is the Earth. The circle is the orbit of the moon. So you're looking top down at the Earth, and then out to the distance beyond the orbit of the moon is this blue thing. That's the actual elliptical orbit that the JWST is in. And all these numbers are in kilometers. So if you look at it as, okay, that's almost 1 million kilometers, and that's almost 1 million kilometers. So how wide is this orbit? This orbit is slightly wider than the diameter of the sun. That's how big this orbit is. So what is it in the other dimension? Well, let's see. Let's look at this thing from the y-axis. Here it is. It left Earth. The telescope left Earth, and it went up in this giant arc, and then it did its mid-course correction to bring it back down. And then it did its final mid-course correction to start it going into this. Now, it's not that thick an orbit. It's just by the time you spin a lot of the orbits, you get this thickened orbital path. So if you're recording a blue line every time it went through an orbital path, that's the shape of the orbit you wind up in. And then if you looked at it in the z-axis, you'd find that, well, from there, it's kind of an ellipse. But notice that the center is not in the center. It's kind of offset to one side. So I referred to it as it's a tilted, bent, offset elliptical orbit that it's in. But it's not really orbiting. This dot here is sort of where it came from, but it's not really orbiting L2. It's orbiting just shy of L2. It gets rather complicated sort of trying to look at this in 3 dimensions as to what's really going on here and why is it bent like that, and why can't it just go around wherever it wants to go around. And I found this lovely video on YouTube. It was posted recently. It's from Launchpad Astronomy, posted on the 28th, and it's only 15 minutes long on your typical in-depth YouTube videos. And he goes into great detail as to why it is where it is, why the orbit is the shape it is, and how often it goes around in that ellipse, and how often it's going to need to maybe fire its rocket to push it into that shape. And the fact that sometimes it's coasting using the gravity of the sun and earth to pull it one way, and other times it's tilted such that that little flat metal panel on the front, the momentum tab, that's actually in a position such that when it gets out to that part of the ellipse, it can actually use that as a solar sail to give it a little bit of push to push it back out. That's why it winds up doing this kind of thing, going down and then coming back up. Because the sun is, as the guy in the video says, the sun is relentless. It's always applying pressure to the bottom of the telescope sun shield, so it's always being pushed out. So you need to not quite be at L2, you need to be just shy of L2 so that the gravity from the sun plus Earth pulls it back down. So it's a complicated orbit, and it's not really a two-body orbit. It's actually a genuine three-body orbit, but the third body doesn't exist. It's a virtual object. So if you've got time, I put that in the email. You can go look at the orbit minutiae. And if you remember, there was a SpaceX crew resupply capsule dock with the International Space Station. It was bringing back a lot of scientific instruments and scientific sample information and data and samples. So they brought that back. It landed offshore, and they've hauled it onto the boat, and they're bringing it back to Florida. And to avoid what happened to Challenger, if you remember, look at all the icicles on the rocket. Is that a problem? Yeah. SpaceX has once again delayed the launch of their most recent capsule satellite launcher. They're launching it for Italy, and they've delayed it now a third time. And there's another launch that's following it, and they're going to delay both launches. So you're going to see two SpaceX launches either on the same day or one day apart from another. So they're, the one that was later is still on target, but the one that was several days sooner is moving one day at a time closer. And the cold weather here in Florida.
Was it the temperature or the wind that they delayed it?
It's the wind, and it's the temperature, because remember, they're not in South Florida. They're up in the middle part of Florida where it will be below freezing. And they're worried about, because if you know, when they go to do the launch, they spray a lot of water on everything. And that water, since it might be misted by the heat from the exhaust, would tend to freeze things. And they just don't want that, because when you freeze something that's under extreme pressure, it tends to not expand too well, and therefore it goes boom. So to avoid Ivanova's boom. And lots of things are taking photographs of the Webb Space Telescope. The Virtual Telescope project has a 17-inch plane wave reflector telescope that they've taken a couple of pictures. They took pictures before it got to L2, and now they have a picture after it's at L2. In the image, the telescope is what they locked onto visually. So they're tracking it by its pixel movement in the imager, which means that all the stars around it are going to be slightly elongated, if not lines. And then they put a little arrow. Look, right there in the center.
Gianluca Massi is in Italy. He normally does presentations about the moon, and we've done presentations with him before.
Yep. And he's using the Virtual Telescope project. So I think it's a telescope that might be, it's either in Italy or it's in Canary Islands. I forget which. It's one of their 17-inch plane waves. I'm going to pull forward an article here. There's another bunch of folks that were also looking at it, and they've got a much bigger telescope. The Keck 1 telescope in Hawaii on the mountaintop. Now they've got some spare time. They've got an instrument that can pick it up. So they also took a picture of it. I would very much appreciate it if these professional astronomers that are taking pictures of the James Webb Space Telescope in the sky would include things like, could you tell me when you took the image precisely and what your right ascension and declination were? I want to know where it is in the sky versus where I think it is in the sky. And until they start, putting out more detail on what they're doing, kind of have to guess at it. Now, I actually mentioned this a couple of weeks ago as what it might mean, but now they've confirmed it as of January 26th. NASA says, hey, given the information we see over the last few years from the Mars Reconnaissance Orbiter orbiting the planet Mars and taking pictures, it looks like from all of the evidence of water that's not there anymore that we're seeing, basically all the geologic contouring of the ground and the colorations and things like that, that Mars had water sooner for a longer period of time, and it took more time for it to go away, for it to evaporate or get eroded by solar radiation than they originally thought. So that's a good sign, because the possibility of there being liquid water beneath the surface of Mars goes up. One of the landers that they sent to the south pole of Mars, it had a little scoop on it, and when it dug below the surface by just half an inch, they saw ice. Now, of course, as soon as the sun shined on it, the ice evaporated. But what that means is there's permafrost down there. So anytime you have water that is there for a longer period of time and goes away slowly, you have the ability to have salt deposits as the water slowly recedes, and you have the ability for biology to get into cracks and nooks and get into cracks that take it to deep caverns, and there may be subsurface water, but we won't know until we bring the right tools and go looking for subsurface water. I still think the best approach is Valley Marineris, land something in the bottom of it where there's known spectroscopic water by way of the hydrogen, and look around in that water, that muddy water that's down there, and see if there's any biology in that. So don't bring so much spectroscopy as microscopy. So pack along a microscope so you can see the things moving around in the salty water. And then, as I mentioned, on our YouTube site, I looked at the management statistics and found that the prior to launch James Webb video that we have had 918 times when I looked at it earlier in the week. And our video on EM drive and photonic propulsion had 124 views, and the Stop Looking for ET had 53 views. These are numbers that are much higher than just our Broward astronomy community. These are other people seeing it publicly on the internet. I summed up all of the likes for all of the videos, and there's 77 likes. 100% of them are likes. There are no dislikes. So that's good that, it's okay for people to go, it was too long a video. I stopped watching it after about 15 or 30 minutes or 45 minutes because it's a 2-hour video. It's okay for them to do that, but I can see the statistics of that. I can see when they leave the site or stop the video, statistics for that.
Well, normally when I play the videos, if I'm watching again, because I'm during the presentation, so whenever I play any videos that are long on YouTube, I play on 1.5, so it's a bit faster. And if they speak very slowly, I play 2.0.
You're not the only one. Yes, there's certain people from other countries that speak, their English is not their primary language, so they tend to slowly enunciate so you can understand what they're saying. And they have the William Shatner poignant pauses between words just for the effect. So yeah, those are 2x when I play back.
Guilty.
Yeah.
The only exception that I speak fast.
So are there any other news items that I missed?
Yeah, I think there was a stage of a rocket that they let crash on the backside of the moon.
Oh no, that I don't think it's crashed yet. I think it's designated to crash soon. It is the upper stage from a SpaceX launch from, I think it's a couple of years ago. When they used the Falcon Heavy to launch something beyond Earth orbit, the uppermost stage that's directly beneath the spacecraft gets jettisoned after it leaves Earth orbit. Where does it go? Well, the next biggest thing that can grab a hold of it is the moon. So the moon gets a lot of our space junk smacking into it is the best way to describe it. So that when they went to launch something that was going to go into deep space, they,
Yeah. There was controversy because I think China has a couple of rovers or something there, and they
Yeah.
were afraid it might hurt
Yeah.
that.
now it's out of fuel. There's no ability to control its descent.
Yeah, yeah.
But what they do is they tend to bring it into a very, very shallow orbit. And sometimes things will fall into orbit around the moon and be there for decades. There is a third stage from a Saturn V during the Apollo era that is still orbiting the moon.
Great. We can have lunar space junk.
Well, I mean,
Yeah.
we already have that. We already
Yeah.
have space junk that's in orbit around the moon that we left. What are you going to do with it?
Yeah.
And number 1 and number 2 left there.
Yeah. So think about the LEM, the Lunar Excursion Module. Well, once it docked with the Apollo capsule, except for the Apollo 13 one, what happened to it? That was left in lunar orbit. Did it fall back? Well, some of them have, some of them haven't. The moon does not have uniform gravity. The moon has dense spots, and therefore you can try and put something into a stable gravitational orbit, but if it encounters one of these dense spots, it can actually bob up and down. And when it does that, it may be in orbit around the moon for decades. So, yeah, there's junk up there. But they don't mention it because, space is big, as Elon said. Okay, any other news items? Okay. I did post the YouTube video, Pulsar Timing Arrays for Gravitational Wave Analysis. That was fun, especially seeing as how I postulated something and they came back and said, yeah, we think this is a thing. I get no credit for it. So tonight we'll talk about understanding two-body orbits. We get into what Helen was really good at explaining to the kids, conical sections. And next week is, by popular demand, extraterrestrials can exist even if you do not want them to exist. That gets deep into the realm of US Navy videos, what aircraft took the pictures, what's a FLIR pod and what are its capabilities. And then the part that most people forget to mention, which is, well, after the Navy released the videos, the United States Senate had the Intelligence Committee get together with the US Office of National Intelligence and said, guys, go back and report on this stuff. What was it? And let us know if we have to do anything about it from a military defensive perspective. So they tasked them with doing that. And they came back with a report. And the report, let's just say, was interesting. It stated a few things that I think were more a matter of fear, uncertainty, and doubt generator, FUD generator, so that the group that was doing the investigation would get more money from Congress.
Yeah, that's it. So the Bellic industry are gonna, milk
Yes,
that cow.
yes. But at the same time, yeah, they left some things outstanding, which would say, you don't know what it is, and you're the military? Should we get some better guys at that job? Anyway, we'll get into that. And then the following week is kind of related to, if you saw last week's where we used pulsars as a means of detecting gravity wave sources and propagations. I thought about it for a moment. I said, why? I mean, we think of pulsars as lighthouses. They spin and, the beam comes by and hits the Earth periodically. We pick that up on the radio receivers, and that's all we think about pulsars. Why don't we use a pulsar as a spotlight? If the radio beam from the pulsar bounced off of an exoplanet, we can use that as kind of a radar. Because if the beam bounced off of an exoplanet and then was directed back towards Earth and we picked it up, the fact that it bounced off tells us something. The wave shift, the energy shift in the beam that resultantly falls upon the Earth, that tells us something. And that shift may actually tell us something about the atmosphere of that exoplanet. or the hardness of it, or whether it's got a gaseous atmosphere. So 2 weeks presentation will be pulsars as spotlights instead of lighthouses. That one I really want to see if there's anybody that picks that one up and goes, hey, we never thought of that. And I signed up Broward Astronomy, AKA Helen and myself, to do another James Webb Space Telescope presentation. I got an email from them, from the Space Telescope Science Institute, saying, would you like to do another presentation? Sure, why not? When the Webb starts producing its first observational data, pretty pictures in infrared of something,
In
not
6
quite sure
months.
what yet. Would you guys like to do the lead up to the public announcement of it? Sure.
All right.
So I
Good.
signed us up to do that.
Very nice.
But what it got me was, since I said, well, I'm going to need to see the data, I went out to the Space Telescope Science Institute's data archive, their massive repository of all their astronomical telescope data. They've got the Hubble Space Telescope, TESS, Spitzer, Kepler, Cassini, every significant not on Earth telescope you can think of in all sorts of wavelengths. They've got all the data from them. And now I have a login where I can just go, okay, what did Kepler see when looking in this direction? I want all the data. And it gives you not just pretty pictures, but it gives you all that juicy numerical data to go along with it. And when I saw that, I said, well, let me go out and look at the James Webb Space Telescope, because they've already got a repository defined for it. And the structure of the repository is defined, but there's no data in it. And I went, wait a minute. They're already recording temperature data from it, from the bottom side of the sun shield and the top side of the sun shield, and the current position of all the mirror segments and the secondary mirror. All of that's data that's flowing back to Earth that I'm sure gets recorded somewhere, because I know that the temperature is available. There's a lot of free YouTube pages out there that are very proud to actively show you, the live temperature of the bottom side and the top side of the Webb telescope. That's data. It's coming in. It's being made available to the public. So I'm guessing NASA is storing it somewhere. Why isn't that in the archive yet? So I sent an email out to my favorite subject matter expert, Will, at Space Telescope Science Institute, and I said, I don't see the temperature sensors above and below as the selectable instruments in the archive. That data is coming back. Where's it being stored? I want to access it. I want to examine the temperature variation on the bottom side of the telescope when sunlight might be reflecting off of the moon onto the bottom side of the telescope, because then it might be brighter for amateur astronomers to take pictures of it from Earth. So I put that little bug in their bonnet, and let's see where they go with it. Okay, anything else before we get started with tonight's presentation? So welcome. Tonight we're going to be discussing understanding two-body orbits. So what's a body? A body is a generic way of referring to something in space. It might be a black hole, a star, a planet, a dwarf planet, Kuiper belt objects, asteroids, near-Earth objects, comets, meteor shower debris, natural satellites like moons, artificial man-made satellites like satellites, and then what's left of them like junk rocket boosters and exploded satellites and satellites that have kind of burned up but not quite, and then spacecraft, whether they have people on board or not. And a body can actually be, if you've got an astronaut doing an extravehicular activity or an EVA, they're actually a spacecraft. They're considered a body in space because they can be affected by gravity, and their gravity can affect other things. So what's a body? Any of these things. I feel like saying it does a body good. Okay, then what is an orbit? So now we know what a body is. Now we want to know what an orbit is. An orbit is based upon gravitational effects that one body has over another, or multiple bodies have over each other. Think of the moon is orbiting the Earth. That's a smaller body being gravitationally affected by a larger body, but they actually have a shared gravitational effect upon each other. So there's never just a simple gravitational relationship in space, even if it's a two-body orbit. Now, an orbit itself is simply the path that something takes as it responds to the gravitational effects. If it's an orbit that is short in duration, then that might be an escape orbit, like something leaving the Earth. It might orbit a couple of times and then do another rocket burn and leave the orbit of the Earth, eventually winding up in orbit around something else. Or it can be a degrading orbit where the orbit is losing out to atmospheric friction or just gravity. It didn't have enough oomph to keep it up there, so it's going to impact the body that it is orbiting. So it's a degrading orbit. The most common orbits are elliptical, having two foci or focal points. There's a special case of elliptical, and you'll remember this from your high school geometry. Circles are ellipses, but not all ellipses are circles. So if you have a circle where the two foci are coincident with one another, you have a circle. As soon as you have a squashed circle or a stretched circle, now you have an ellipse. But even when it was a circle, it was still an ellipse. You just had focal points that were coincident. So due to the varying densities of the body that you're orbiting, the orbiting body's path is more likely to be dynamic. Not a perfect ellipse. It's got what is known as perturbations in it. Anytime your orbit is low enough that as you pass over the surface of a larger body where you have a denser spot, your orbit may actually dip slightly and then come back up. That happens when objects are in low Earth orbit around the Earth or the Moon. And then you have some orbits that are not even a closed loop. If you're orbiting asteroids or comets, where you don't have a reasonably uniform density of the thing that you're orbiting, or it's an oddball shape like a multi-lobe asteroid, or it's potato shaped, and you're orbiting it around its longitude, you may actually just be in a continuously tilting corkscrew and it winds back on itself, kind of like if you have a paper tube and you're winding up some twine and you just wind the twine back and forth. Sure, it'll overlap, but it'll always want to move up and down the object. There are actually orbits like that. But we're going to focus on the more regular orbits. So why are we only talking about two bodies, one smaller body and one bigger body? It's a math complexity thing. It's pretty simple. You can use trigonometry and Keplerian and Newtonian mathematics to calculate your two-body orbit, except the dynamic ones. So we'll leave those out at the moment and just say it's a uniform gravitational object that we're orbiting. But there's actually Wikipedia stuff on the two-body problem, and then it's bigger brother that they use supercomputers to figure out. Actually, they use supercomputers for all the orbits nowadays, just to make sure they're precise and they understand all the possible effects. So everything is an n-body problem when it comes to space exploration, and you want to get the target where you expect the target to be. You want to do that rocket burn to exactly what you need it to be and not any more, because you'll waste fuel or you'll put yourself somewhere you don't want to be. And typically a two-body system, one body will be very, very much larger than the other body, more so than, let's say, in the case of Pluto, Pluto and Charon are close to being the same size. So the center of mass of that two-body orbiting system actually is above the surface of Pluto. we're not going to be talking about those where the center of mass is the barycenter, as they call it, is above the surface of something. All of our barycenters will be below the surface of the larger object, just to keep things simple. But there are other, not just but three-body systems. If you're into Star Wars and you understand Tatooine, then Tatooine has two suns, and Tatooine, the planet, has a complicated orbit that goes around both of them. But they don't get into the complication of the details in the Star Wars movies, because one of the stars that it's orbiting would actually be very, very hot, and the other one would be farther away. And then you have very much in-body systems, like the stars that are orbiting close to a black hole in the center of a galaxy. In the center of our galaxy, we have a black hole called Sagittarius A star. And Sagittarius A star, I think they've monitored 26 stars that are within the gravitational field of the black hole. Obviously, you can't see the black hole itself because it's a black hole, but you can see all the stars. And as they get sharper and sharper images of this group of stars orbiting the black hole, they find that it's not 20, it's 21. That's not 21, it's 24. It's not 24, it's 26. So they keep finding smaller stars that are in defined orbits around the black hole. So here's the scope of the orbits we're going to discuss. We're going to stick to orbits where one body, the orbiting body, is far smaller than the body being orbited. So you can think of it as Sun, Earth, Earth, Moon, or Earth and a satellite. We'll stick to sustained, not terminal or escape orbits, not orbits that are going to crash on the surface or leave a planet. And we'll stick to the closed loop orbits, the ones that, every time it goes around, it's pretty much in the same place. It's not corkscrewing around and such. We'll stick to predominantly the elliptical orbits, but even the elliptical orbits that are very close to being circular. For example, the orbit of the Earth around the Sun is not perfectly circular. Neither is the orbit of the Moon around the Earth. People just kind of think of them as circular, but there's a variance. So they're measurably elliptical, which gives you we think of it as when the Moon is far from the Earth, it's apogee. When it's close to the Earth, it's perigee. But there is a more generic term called Aphiosis and periapsis that are literally saying when it's close and when it's far. That's what you get from an elliptical orbit. And here we get into conic sections. So how these orbits look is exemplified by simple geometry. So if you have a hollow cone, and then you take a plane and you slice the cone, if you slice the cone with a flat plane at 90 degrees to the vertical axis of the cone, you get a circular orbit. It doesn't look circular in this picture. That's just 2D to 3D distortions. But if you tilt the plane, still a flat plane, but if you tilt the plane, you get an elliptical orbit. So you can think of it as if the inclination of the orbit is near zero, then you're going to have more likely a circular orbit. If the inclination of the orbit is tilted, it's inclined, you're going to have a more elliptical orbit. Now, there are other kinds of orbits that are non-terminal. They're not closed loops. You have parabolas or parabolic and hyperbolic or hyperbola orbits. That's as if you take the flat plane and you tilt it almost vertical, and you get kind of a grazing slice off the cone where not all of the orbit fits within the surface of the cone. It might go off the end. We're not going to talk about those. Those are useful for gravity assist and for escape orbits, but we're not going to cover those. And we're also not going to mess with the really oddball one, which is, okay, that cone, what happens when the cone itself is not right circular? In other words, when the cone is not facing vertical, but it's slanted. Well, when you intersect the plane with it, you can get variations in the orbit, which resemble the same effect as if you change the inclination of the intersecting plane. But knowing all these shapes and how they interact with one another is why orbital parameters are not just, a couple of parameters. It's a bunch of parameters. And if you really want to define it in three-dimensional open space, it's even more parameters. But what about when the cone is rotated? So if we squeeze the cone and then we turn the cone around, but we still leave the central axis vertical, that can also change the shape. And you get that when you have a different gravitational field. You have a non-uniform gravitational field, like one of those potato-shaped asteroids. You can get, even though your craft thinks it's got zero inclination and it wants to be in a circular orbit, the gravitational field of the thing you're orbiting says, nope, you got an ellipse. So we're not going to get into that specific thing, but there is one orbit we're going to talk about, which is if you have a highly elliptical closed orbit, then you can rotate the orbit so that the nearest point is above a specific place on the thing you're orbiting. Spacecraft that are used for communications with Russia are very much aware of this orbit. It's called a Molniya. And when it wants to do observations in space, it is at that very far point in its highly elliptical orbit. So it does its thing out there, saves the data, and then it comes back. And as it comes back, it's going to be at its lowest point in its orbit, right above the satellite receiving station. So you can send all the data back. And that's quite popular when you want to have a very elongated orbit where you're doing some science out at the end of your orbit, and then you're bringing the data back, and you want to have the fastest transfer time. Kepler was an example of that.
So the other kind of Molniya orbits is for TV satellites in Russia, that they do the opposite. They keep the satellite pointing to the transmission stations when it's farther apart because it has a wide field of view.
Yes.
And then moves very slowly, takes hours for you to go up to the top of the orbit. And then when they are close to Earth, it's the opposite side of the Earth, and they move very fast. So the satellites keep communication constantly.
But what they have to do is put a slight variation in the orbit of the satellite and have multiple of them so that you get continuous TV coverage. But your satellite receiver has to be smart enough to know to switch between the transmitting frequencies between the two satellites, and also as a backup. But yeah, it's used for the United States, and even for South America. We'll put a satellite in geostationary orbit, and it will just sit there directly above, kind of a bit south, and the radio footprint will just cover the entirety of the US. That's why whenever you look at DirecTV satellite antennas, they're kind of all pointed in the same direction, because that's where the geosynchronous satellite is stationed. But if you live in other parts of the Earth where you're not close enough to the equator for your satellite, you're a very high latitude or a very low latitude, then you have to get into putting up multiple satellites with a reverse Molniya, where it's got a footprint over the area because it's very high up and moving slowly at the end of its apogee. But that's why we have all these different parameters to define an orbit. It's not just a simple circle. Here's one that I was not aware of, but I found out that it's actually a thing. What happens when the intersecting plane is making your conical section and the plane is not flat? This is how the James Webb Space Telescope works. If you looked at that picture of the orbit, it was kind of bent in the middle. It's almost like the intersecting plane is not flat. It has a curve to it. And the only way I could come up with an analogy is kind of like a roller coaster. if the thing that you're orbiting contributes gravity, if you have propulsion ability, you can maintain a semi-stable orbit at a Lagrange point or near one like L2, where in a certain part of the orbit, you're letting the gravity of the orbit of the object you're orbiting pull you back. And then since you have the ability to have a giant sun shield on the bottom, you're letting the solar radiation, radiation reflection pressure push the spacecraft farther out. So you have this sort of swept orbit, but it's an ellipse in the other axis. So that's another variation, is you can have the intersecting plane not be flat. So here's some common elliptical orbits. You've probably heard of these. Low Earth orbiting. This is where you want to have the minimum transfer time between the surface of the Earth where your transmitter is and the satellite receiving antenna, and then back down to the Earth. So that's why Starlink satellites are in low Earth orbit. Is transit delay of the radio communication. Then you have ones that are a little higher. They're not quite up to the Van Allen belts, which would be bad news for the electronics, but they're a little higher than low Earth orbiting. This is when you want more than a minimal footprint. You want, as the satellite goes overhead, to have a not countrywide, but certainly a couple of 100 miles wide diameter footprint, so that it moves over the area a little slower by being higher in orbit. That's your global navigational systems, or your GPS satellites. Those are in higher orbits, and they're circular because you want to keep your distance the same for your GPS satellite as it goes over the curvature of the Earth. Then you have the geosynchronous, which is it just rotates with the Earth. And then you have the special form of that, which is it stays above the same spot all the time. That's the geostationary. And the two terms are not really interchangeable, but people tend to confuse them, because you can have a geosynchronous satellite that's polar orbiting. It's not above the equator. But if you have a geostationary satellite that's above the equator, it's your favorite DirecTV satellite.
Rotates with the Earth and always stays above the same spot. That's not the same thing?
No. Geosynchronous is the one that just rotates with the Earth, but you can rotate at the speed the Earth rotates and be at an angle. You can be inclined. But if you want that satellite to always be in the same spot overhead, you need geostationary. So it's geosynchronous in its speed, but its inclination is near the equator.
Okay, thank you.
Yeah. And then you have scanning or surveying observational orbits. You'll often hear these referred to as polar orbits or sun synchronous orbits. These are ones where if I'm in a orbit that's slightly slower than, in other words, slightly higher than geosynchronous, then I'm very slowly moving around the Earth. And the Earth may actually be rotating faster than my orbit. So I've got the Earth spinning faster beneath me than I'm orbiting it. So I can actually do sweeping scans of the Earth just by hanging out and just leaving my observation camera or radio or radar on, and the Earth will actually paint itself beneath me. And then you have the high inclination, highly elliptical orbits, the Molinias that we pretty much already discussed. Therefore, special observations where you want to improve the data transfer time by being very close to the Earth, or close to the Earth when you're transmitting the data, or you want to be very far away from the site you want to cover because you want to be moving very slowly over that area to have a very large radio footprint. And as I mentioned earlier in the news part, but this gets it into the recorded presentation. Here's the non-flat plane elliptical orbit of the James Webb Space Telescope at, but not quite at, almost at L2, the Sun-Earth Lagrangian point number 2. The width of the orbit is actually larger than the diameter of the Sun. the height of the orbit is actually almost the height of the orbit of the Earth around the sun, and the z-axis is almost a perfect, nice oval ellipse, and it kind of uses gravity to pull itself down towards the Earth, and then it uses a rocket firing to get itself back up into the orbit, and it uses its momentum management, that flap on the front of the James Webb Space Telescope. Model here. That little black flap at the front, this thing. The sun shines off of that and adds to a particular angular push. So if you can think of the Webb telescope, it's actually kind of bent in the center like this. So that flap is actually going to be used to push up so that the orbit goes high in the ellipse, and then the sun is going to be always shining off the bottom of it, and that's where the solar panels are to power it. So it's going to want to push it out that way. So it gets down to the bottom by gravity, and then it gets back up to the top by sun and sun. And then if it wants to tweak it just a bit to kind of like bring it back down over the top, then it'll fire thrusters on the bottom to do that. But sometimes it'll have to fire those thrusters, sometimes it won't. But they estimate that about every 21 days, they're going to have to make an evaluation of, do we fire the rocket and how much and in what direction? And that's where the supercomputers come in, they're taking into account all of these effects. I found out they're actually taking into account, didn't know this was really in effect, Jupiter. Jupiter being the big behemoth in our solar system. There's actually an outward pull because the Earth goes around the sun faster than Jupiter goes around the sun. Every time the orbit plane of the Webb telescope approaches Jupiter and then goes past Jupiter, it adds an additional gravitational effect that goes into their calculation. But there is a difference between astrology and astronomy. In astronomy, it's a known gravitational effect. It's not going to affect your psyche. It's going to affect the spacecraft.
The Lagrange point is a very delicate area. It's almost like if you look at space-time, that would be a flat area. So any disturbance in the force would change the trajectory of the spacecraft.
Yeah, they're actually counting on the gravity of the Earth and the sun to pull it back at the bottom, down here at the bottom. So the way it moves this direction is by the gravity of the sun and Earth combined. So it's being pulled back down. L2 is actually out here. So it's not actually orbiting at L2. And
it actually falls in direction of the
yes,
L2.
Yes, under gravity from Earth and sun, it falls towards it. And then it uses the radiation reflection pressure to push it back out, and it tilts itself. And when it gets to the top, to get it started back down, kind of like the roller coaster, it'll maybe fire its thruster to push it downward a bit. And it's going to be doing that off and on for the next, 10, maybe as long as 20 years. So every 21 or so days, it may have to like burn for a few seconds on that rocket, which consumes its fixed amount of fuel, which will be the ultimate determiner of how long the James Webb Space Telescope will be a usable astronomical instrument. Because once it gets towards the end of its fuel, they've got to shut it down from doing astronomical observations and use the remaining fuel to kick it out of its L2 orbit into a more traditional orbiting position, where it might actually wind up at L5 or L4 and then continuously just orbit the sun.
Monroe,
yes.
I found a way to actually show this picture in a way that would be kind of visible, because it's flat plane, sometimes it's a little bit more complicated. So sometimes it's better to have something to observe. So if you look at the first picture, it's like you're looking Earth from the North Pole, and the orbit is something like this. So Earth would be here, and then you would have the orbit being a little bit tilted, like this was bent, but it would be like this. So as it goes down, it falls into L, and then you need the spacecraft to actually push up and have this. So that's the way you look at the first orbit. And then this is like you're looking on the top of the orbit. The second picture is actually almost the same position. It's like I'm flipping like this, so I don't see the orbit of the moon. And then you can actually see that the line, it becomes like very straight, because before, if I turn like this, you would see something like this. And it's it would be from the top. Now, what you're seeing is if I flip, this is from the bottom. So you flipped, and so this is almost the same way that the scene, just one is like this. So you can see from flat. So if you look at the Earth picture on the second picture, you can actually see the orbit of the moon is a little line. So that's what you see, something like this. And then the other picture, the z-axis, is like I'm looking this like this.
Right.
So that's the way like this. So it makes easier for you to observe how it would work. But this would be like straight like this in the glass. It's like this glass was kept like a little bit broken, kind of, you know, bent like this.
And also it would be above the
way for
center.
you to observe the picture using, you know, something that you have in your home.
And also the bottom of the glass would be above the center stem, because you notice that it's shorter here than it is up here. So it's, as I referred to it, it's bent and it's tilted and it's shifted.
Yeah, it would be like if this would be like this, but then this could still be straight, just like, just shift.
You know what we need to do? We need to melt one of those glasses we received on New Year's, because they're made out of plastic.
No, I have a better idea.
What's
A
that?
wire. Use a wire.
Yeah.
Like a little wire, you bend like this and make, you know, like a little wire.
Being somebody that once did 3D animation, I understand the 3-view, the tri-view. So x-axis, y-axis, and z-axis. But yeah,
that video you noted about, would that explain it?
So what?
You talked about a video, a YouTube video.
Oh yes. This guy right here, this YouTube video, very good. The actual title of it is "How JWST Orbits Nothing."
Yeah.
Because it's not actually orbiting L2, it's orbiting a virtual position. So if this is L2 here, what it's actually orbiting is closer to Earth than L2 is, but not by much.
It's basically falling on L2, but as it tries to fall, the gyroscopic move away from it, and then you need the spacecraft using the combustible to move up. So it moves up very difficultly, like, you know, you're in a roller coaster.
No, it
and then
doesn't.
when you
It
go on
doesn't
top,
use,
falls back on the L.
no, it does not use the rocket to move up. It uses the radiation reflection pressure on the bottom of the spacecraft combined with that tab as a continual force. That's what moves it up the curve. So if people say, you can't move things with sunlight, yes, you can. That's what makes it go up. Down is gravity, up is sunlight. And then when you get to the top, to avoid like just continuously going off the top edge, you have to fire the rocket to push it back down the other side of the roller coaster. Yeah, watch this video. This video, he does a pretty good job of it. But if you want the numerical characteristics of the orbit, then you can go to the actual Space Telescope Science Institute halo orbit explanation. I always knew that the width of the orbit was fairly wide, but when I did the measurements here, I went, let's see, that's 800,000 kilometers. That's 800,000 kilometers. That's 1.6 million kilometers. The sun's diameter is only 1.39 million. So the width of the orbit is actually wider than the diameter of the sun. Anyway, you never know how much you're going to learn until you learn what you didn't know.
It's probably impossible to really visualize it to scale.
Yes, I've tried doing it with the OpenSCAD 3D modeling software, and it's a challenge. It's a challenge. But I actually have a model that I'm going to be showing us that gives you the basic understanding of orbital planes and intersecting planes and ecliptical and those kind of stuff. So once you have something moving in an orbit, how do you describe the orbit? There's two means of doing this. You can make assumptions about what you're orbiting. So for example, if you say, well, if the thing I want to describe the orbit of is always orbiting the Earth, I can make a lot of presumptions about, how big the Earth is, how much gravity field it has, how fast it rotates, where it is in the solar system, what kinds of other things affect it gravitationally. So I can make a lot of assumptions, and that reduces the total amount of stuff I need to say, and this orbits this way, and this one orbits that way. So I can reduce that down to, it says 2-line elements. It's actually 3 lines of text. The first line of text is just kind of the name of the thing that you're describing, the satellite's name. And then you have 2 lines that describe the orbital characteristics of it. And then if you say, well, what if it's out in open space, kind of like the James Webb Space Telescope, where it's orbiting a virtual nothing. There's no planet that it's orbiting. How do you describe that orbit? Well, that not only requires a lot more parameters, but it requires you to update the orbital parameters every time you fire your rockets, every time you get to the bottom and want to go back to the top, because you're bending, you're changing things. So you have what are known as oscillating elements. This is just something is orbiting something else, and it will be that until it changes. So they just refer to that as.
In physics, we always do that. We do frame of reference, because then you remove stuff that you don't need to simplify your calculation. So you reduce the parameters of your equation so you understand whatever you're studying. So when we do motion, we normally do frame of reference. This from Kepler and Newton. So all the problems that you learn with the 3 equations that you use for the Newton laws, you always do a frame of reference. That's like the first step for you to understand anything in physics. You need to reduce with whatever specific you need. So you do frame of reference to understand your problem.
When you get to wackadoo orbits like virtual orbits and halos at L2, it's kind of like, well, you need the full set of numbers, which I ran into with some of the planetarium software applications. They only wanted to know about, things that had lovely flat, circular, or maybe slightly elliptical orbits. So they would take the TLE data if it's a satellite, and then they would take a subset of the oscillating elements. When you include the observer location as a presumed item, you can just call them the ephemeris. But the big picture, when it's open in space and it's a bizarro orbit and you've got them all the parameters, they just refer to as the oscillating elements. Now, the TLE, once you have the full set of oscillating elements, you can use some presumptions and you can derive the TLE from the oscillating elements, but not the other way around, because the TLE doesn't have all the data. You can't synthesize oscillating elements from a TLE. And every time you have a course correction, sometimes there's simple mid-course corrections on the way to something. I think that the New Horizons did something like 14 course corrections on its way to Pluto. So every time it did a course correction, or every time it flew past something, you had to update the oscillating elements. Webb's going to have to do the same thing. Every time it peaks out on one of its elliptical orbits, or every time it fires its thrusters, it's going to have to put out new oscillating elements, and certainly new TLEs for those people that want to simply just plug it into their satellite viewing stuff.
I just look at the definition of oscillate. I like it. So when you see those 2 planes in the picture touching, that's an oscillation. The other meaning of oscillations is kissing. So when you touch it, something that has the same tangent.
Yep. The other bizarre thing about it is you can actually have what I found to be defined as a slippery orbit. So you're not just orbiting something, you've got a little extra sidekick in there where your orbit is actually rotating. And that's why you need the oscillating elements, because it's not just the simple frame of reference. Is your frame of reference is constantly changing, but it has a known defined change rate, a rate of change, and therefore it adds additional parameters. And then you've got to say, well, here's my oscillating elements, and where is the orbiting thing right now? Where's the beginning? You can either say, well, as of me producing this data, this set of data, it's right here. And you can define its location within its orbit. Or you can say, well, here's the orbit, and here is the closest approach, or basically here's the apogee point and the perigee point, and it's as of right now. I'm telling you that the fractional year, the date, time is as of apogee or perigee. So I can have a time of apogee, a time of perigee, and they can be kind of the same thing as saying it's today and it's at this point in the orbit. So there's several different frames of reference you can have for passing along your oscillating elements.
Basic, what you're saying is that oscillates perturbations on the orbit. When
Well,
another body kind of changes a little bit the other, right?
More so than that, you have all kinds of things that can affect the orbit, and all of them create perturbations. How close you are to something, how far you are from something, the angles at something, all of those are elements that can cause perturbations in the orbit. So they just collectively refer to them as oscillating elements. You have a long list of them. Okay, this is my favorite little 3D CAD program, costs no money. I always like things like that. OpenSCAD. Here's the plane of the ecliptic, this gray plane here. And I even got the text to look. Text works fine now. I can go underneath it and it says it correctly, left to right, backwards, forwards. So that's the plane of the ecliptic. And then I have the plane of my orbit. So that's the slice into the orbit there. You can see that they intersect. And then I have the shape of my orbit. I have my two focal points here. The thing that I'm orbiting is usually at F1. And you have the other focal point, if it's an ellipse, which is offset. So that will be closer to one of the limits of your orbit. And then you have the thing that is orbiting you, which is, where is it? It's right here, right now. So you need a particular time at which that occurs. So that's the kind of a 3D model of the plane. But one of the neat things about this program is I can go in here and put in little true false Booleans for showing things. So I can say, why don't we hide the ecliptic plane? I just click there and look, it disappears. And then I can say, hide the orbital plane. And it's gone. So now it's much easier to see, here's my orbit, and it's tilted, and it might be rotated. And there's my two focal points, and here's my object orbiting it. So now I need a bunch of parameters. And if you look over here on the right of these small numbers, we'll get into what they mean, but these are the parameters necessary to say, and here's my orbit. And a lot of them have a whole lot of decimal places. And the reason it needs a whole lot of decimal places is space is big. This thing is very small. So you want to precisely know where it is and when it will be where you expect it to be, which is why you have so many decimal places. And just for grins, I can say. And,
what is this drawing program called?
It's called OpenSCAD, OpenSCAD.
Thank you.
It's free software. If you just Google OpenSCAD, you'll find it. I used it initially for doing 3D modeling for my 3D printer. So I would create the models here, and you can put the numbers in directly. Let me show you here. So you can put the numbers directly into the software. So when I look at what's the value of my inclination, here's the value directly out of the NASA Horizons Solar System Dynamics values. So I can plug that in here, and that's my value for I. But then I can scale it and say, well, what's the inclination of that thing? So down here, I'll have my orbital plane, and you can see that it rotates in the x-axis by I. So even though the 3D modeling stuff that I do is for my printer is usually in millimeters, it has no problem being open scale. So it's just numbers. They're all compared to one another. So these can be very enormous numbers or very small numbers, and it knows how to scale everything. And it's just, it's, if you think of it as, if I wanted to draw an ellipse and I wanted to draw it at an angle, I need to make the pen move a certain way, and I want to draw things. So if I wanted to draw, let me turn the planes back on. Here's my planes. My plane of the ecliptic is nothing more than a very thin cube. A square is a quadrangle, but not all quadrangles are squares. So if you have a quadrangle with equal length sides, then you've got a square. But the same thing holds true in all this 3D stuff is when I draw this flat plane, if I make the plane very thin, then it essentially becomes what looks like a flat plane. It's very thin. But if I want text, I'm 3D drawing text. So I go in here and say, I want my text to be black. I want to slide it over so it's here on the edge of the plane. There's no rotation because it's going to be in the plane of the plane. And the text is all two-dimensional. So if I want the text to be three-dimensional, like you see here, you can see how the text has height. Then I go in and do a linear extrude. I actually draw the 2D text and then stretch it vertically. So I can do all that kind of funky stuff. It's kind of like Google Earth or the Weather Channel. If you're into it, you can spend hours just playing around with things. But since the software doesn't cost you anything, and if you're retired, it's just your own time. So I play a lot with OpenSCAD. Okay, that's OpenSCAD. So you can do 3D modeling of orbits. So if you go out to the NASA JPL Solar System Dynamics Horizons website, you can get oscillating elements for things. So if you want to know, give me the orbital parameters for the James Webb Space Telescope, it comes out with this whole bunch of numbers here with lots of decimal places in them. They're very accurately calculated, including the time of day. So that's the values. If I wanted to see the Gaia spacecraft, which is also at L2, I would get the same quantity of numbers, but they'd be different values. And if I come back a month from now and ask for it to generate them again, I'm going to get slightly different values, but the names of all the parameters and what they mean would be the same. Whenever you go out to the Horizon site and you say, spin me up some of these numbers, it produces a report. And then you can go download the report, look at it, and at the bottom of the report, it actually gives you an explanation as to what all these labels mean. But the software that you're using the data in may not be able to digest scientific notation, which is what all this stuff is. When you're doing science, scientific notation works. So you don't have lots of zeros and decimal places being in different places. It's just if you can handle scientific notation, you can handle any number you want. So the Horizon site always spits things out in scientific notation. But if I want to input that to Stellarium or Starry Night, I have to use normal decimal notation with lots of decimal places. This is the actual web link that would produce these values. And you can see the parameters in them, like what's the start time? When do you want me to calculate this result? What is the object that I'm telling you to go look at? It's -170, which is the object ID for the James Webb Space Telescope. Where are you looking at this from? Let's see, my center is 500 at 399, which is I'm looking at something that's heliocentric, the sun, 500, as viewed from Earth, which is object number 399. Everything's, you're not going to use labels here because this is very old parametric software, so it likes to use numbers for things because numbers can be open-ended. If you called it a moon, is that a moon or is it the moon? So that's if you want the full boat oscillating elements. Now, if I want just the satellite tracking, the 2-line elements, which are actually 3 lines of text, then I can go to a place called Celesttrack. I can, if I know the ID number or the name of the satellite, I can look up any satellite I want, including all of those SpaceX Starlink satellites, 2,000 plus of them. All of them are in there. They're all tracked by the US Space Force, Space Command, NORAD ID numbers. And they actually are running out of precision on these numbers. If you note, the columns of all the numbers in a TLE are the same. I used a fixed font so I could say, well, let's see, the U is in this particular column. So no matter what the satellite is, the thing that says it's a man-made satellite, that letter U goes right here on the second row. So they're in fixed positions, as opposed to the previous one, where these are labels. So you have label equals space number. That can be anywhere in the output, but as long as you know what the label is and how to find the actual bounds of the numeric string and process it, they can change all that all they want to, and they can put new numbers in, add things, shift the columns around, and you can still know how to process it. But these are old ways of doing it. This is dating back to we had computers running Fortran 2. When we were putting things in orbit for the first time. So everything is column dependent as to where you'll find certain parameters. And the column numbering is different for the 2 rows, because you can actually see there's numbers out here that aren't, they're not equally spaced because they needed more digits here than they needed there. And there's a single digit number here, and they had to keep it to an 80 column card. Back when computers passed data on punch cards. So if they could use a larger card, then you'd probably only have a 1-line element, but they needed to split it apart. So here's the object ID being repeated. So the title of the thing is James Webb Space Telescope. This is line number 1. You can tell it's line number 1. So if you actually get your card deck shuffled, that's line 1. This is line 2. And you can see it's for the same object, 50463. So if it doesn't have a number, it's the name. If it has a number, it tells you which row it is. And then the ID number will tell you which one it is. So you can correlate 5063 back to JWST. But you see the hole? The hole is, okay, it's JWST. But where do I cross correlate JWST to 50463? There should be like a 50463 up here. Where were you when we needed you? They didn't think to do that back then, and they've just kept with it for backward compatibility. But because they're running, see, it's a fixed number of digits they have here. And when you've got guys like SpaceX Starlink putting 1,000 plus satellites up there, you're going to run out of digits. So there's a new format that's going to be XML based called SGP4, Simplified General Perturbations Model for Orbit Propagator, or SGP4. That's the new way of describing orbit mean elements messages. The OMM is actually a TLE grouping of these 3 lines is called an OMM. So when you reformat this for SGP4 and you put it in XML, it's going to be much larger and there'll be labels on everything. So that's what I have to look forward to in probably the next year, is migrating all my older software from TLE to SGP4 in XML, or converting it using data in applications. So if you've got planetarium software that can show you where things are in the night sky, you want to do what if scenarios, you've got to get all this orbital stuff into the software for it to know where things are in space. And they're not going to take just any format. Those applications have software developers that wrote it for a certain format. And it's got to be in that format, no questions asked. It is in that format, or bad things happen. It'll either give you an error or the application could blow up. You have to start it over again. So whatever format the data is available to you in, like Horizon's format, you have to translate that to the format that your application wants. And I've spent time in my career writing adaption applications. So taking data in one format and converting it to another format that a different application wants is, I've done that in many programming languages, and I did that in an Excel spreadsheet using Visual Basic for applications. So I could take the Horizon's oscillating elements data and produce asteroid data for Stellarium and Starry Night. So I take the oscillating elements, and this is what I spit out for Stellarium, because this is the format Stellarium wants for a sun orbiting asteroid or comet or near Earth object. So it wants these values. You can see some of these are readily recognizable, like inclination. That was that IN value, and it's got the same value. But notice it's not in scientific notation. It says a decimal number with lots of fractional digits. So take the value you get, reformat it to be the value that it wants, put it in the file at the location it wants, and then fire up the application and say, go read the file. Or when you're doing startup, there's where you can find the file. And it will read this in, and all of a sudden, voila, now you've got a James Webb Space Telescope that Stellarium can show you where it's going to be from night to night up until 21 days after its last orbital burn, and then you've got to do it over again. Now, if I only had to do it ever once, I'd probably do it by hand, just hand crank out the text file. But seeing as how every 21 days it's gonna change, I used an Excel application to do that. Now, funny thing is down here, if you make a reference to a textural map of no map, there is a default mapping. So when you zoom in up close on your James Webb Space Telescope, it's going to look like an asteroid. It's just a glowing fuzzy blob, almost like a star with a very small glow. And that's if you made it no map. But if you take an image of the James Webb Space Telescope sitting out there at L2 and you shrink it really small so it fits within the confines of what they want that texture image to be, now when you zoom in on your JWST and your Stellarium, it'll actually show you a little tiny picture of the James Webb Space Telescope. And I've created one of those. It's called JWST.png. It's just a little tiny James Webb Space Telescope. So that's Stellarium. Now for Starry Night Pro Plus, it's a little different. You don't just create a file and say, go read the file, or at startup, here's where the file is located. You have to actually go in there, manually enter the data the first time, and then it will remember it. So you'll have your Excel spreadsheet with the data on it, and you'll be copy, paste, and you'll paste the values in to where it expects to see them. And then you submit the form, and now you have a heliocentric asteroid. You have a sun orbiting asteroid that shows up in Starry Night. And then 21 days later, you've got to enter the data again, which is a bummer. At some point, the Starry Night folks are going to make it where it will show up in the periodic orbital updates that Starry Night has. The problem is Starry Night doesn't have the algorithms to do one of those funky elliptical, squished, tilted, uplifted orbits. It doesn't have the algorithms for maintaining that. So, my Excel spreadsheet will come in handy, and I'll just delete the asteroid and then put it back whenever I want to have a current, observing session. So, in conclusion, current orbital data is available from a number of sources on the internet at no cost. And the automated data request, if you want to write something that will go, punch an internet web request and spit back the data, you can write a query request that will do that. But the query may not just produce the raw data, it may actually produce a report that then you have to download, and then you have to extract the data using a software algorithm to go find the labels or pull out the fields. How much of the data is actually needed and in what format is going to be varying based upon the application and what type of object you're loading into the application. Are you loading a satellite or an asteroid or a comet or a near-Earth object? It's possible to remap this by hand if you only have to do it once, but if you have to do it again and again and again, then you probably want to invest some time in Python or Visual Basic for applications in Excel, and just punch the button, have it go get the data, reformat the data, and then you copy and paste it into a file and you're good to go. That way you don't have to play with the algorithms every time. Once it's understood, now your astronomical software can tell your computer-controlled telescope mount to go point at it, because I doubt that your hand paddle of your telescope will be constantly updated for, in its wackadoo elliptical orbit, where's the Webb now, as of right now. So if you can load it into your application and then have the application tell the telescope, just point to this right ascension and declination and you're done. And I think that's actually what they're doing right now with the professional telescopes, is they have some application that goes off and does the orbital calculations, and then just comes up with as of right now, here's your RE index. Punch them into the telescope, go there, there's your field of view, image lock it on the dot that's, if you lock on that dot, the stars move, but the thing you're tracking doesn't move because it's image locked by pixels in the image. And so that's how you take pictures of things that are moving really fast across the sky. And nowhere did I give you any quadratic equations to explain orbital characteristics, but yeah, when you get into in-body systems, there's some heavy quadratics out there.
Oh, that would be nice.
Yeah. Well, there are places on the internet you can go find that stuff if you're into that. I was into that when I was in school, and as I left school, it's like, oh, the brain gets fuzzy. I'll stick with the stuff that's current.
Or if you want to find anything and calculate anything, you ask your friend's programmer to do that.
Well, I am a programmer. I understand math and I can read documentation. So sometimes I, blow the dust and the cobwebs off of it, and I go do integrals. And when I'm doing the 3D modeling stuff, I do that. But sometimes I take the cheap way out. So next week we're going to be discussing our friendly neighborhood aliens, and when we do that, and we're talking about the Navy videos, it's also a discussion of, and the F-18 was at this banked angle and the object was down here. It's like, I need a model of an F-18 aircraft. And here I have, Helen would like this, about 12 different little pieces of stiff paper with printed things on it. And I'm going to be gluing all that together to make a little tiny model of the F-18D aircraft.
Why so small?
Well, it has to, if I make it too big, then I have to hold it out here somewhere.
Yeah.
And besides that, the particular size that the model is, all fits on an 8.5 by 11 sheet of, dense print paper. It's 110-pound paper, so I can print it out. And then I have to use my X-Acto knife and slice it all up. But it's in multiple layers, so it'll actually have a three-dimensional shape to it as I stack the different pieces and I super glue them together.
But by the way, I'm having a lot of difficulty to actually understand the physics of the Lagrange orbits, because normally what I study was the stationary bodies on the Lagrange. That's what I understood when I did my physics courses for the Sophia. And the James Webb Space Telescope is something really new that I'm still not quite grasping how, like, the explanation of the simplification of space-time doing on the Lagrange point for that kind of orbit.
Watch that YouTube video, how the Webb telescope orbits nothing. That's very informative to explain it, how it, goes up and coasts down, and where it uses the momentum wheels and how often it has to fire the rockets, and all that stuff is explained in the video. He does a really good job of it. I don't normally watch his videos, but this is a really good one by him. I just happened to stumble onto it.
Can you post that video on your library or on your page or on your Facebook? Because that's very good source of understanding material, because this is very complex orbit. So it's like a little bit above my pay grade.
Oh, your pay grade can be elevated.
Okay.
Monroe, have you run into, in any of the software that you're using, limitations on the number of decimal places allowed?
No, they all seem to use Microsoft 128-bit floating point on the internal. So
Oh,
I can do 11 or 15 decimal places and have no problem.
nice.
Here you go, Helen. So did you see the YouTube link that I just posted?
Yep.
In the chat window? Yep, that's the YouTube video of how JWST orbits nothing.
Ah, great.
It's only about a 15-minute video, I'd say. Sit down with your favorite beverage and watch it, because it's interesting. He explains it sufficiently that by the end of the 15 minutes, you know why it's complicated. Gravity and sun, and and also it gets into the issue of the momentum wheels can only be spun up so far, and then they run out of RPMs, and you have to spin them back down again. So that ability and how fast it can run up is actually related to the upper and lower limits of that curve. And as he says, the sun is relentless. It's always applying pressure to the bottom side, but it's also applying pressure to that tab. So it doesn't just push it out, it pushes it out and up.
Are you at all surprised as to how smoothly the deployment of James Webb has gone?
You mean owing to NASA's normal whoopsie, I am amazed at how well it's gone. But
Me too.
on the other hand, it's not done yet.
Yeah, but so
No.
far, all of the many, many moving parts and all of that has apparently gone perfectly. I'm quite surprised.
320 actuators have all performed perfectly, or
Yeah.
as they say, nominally.
Yeah.
Yeah, I'm somewhat surprised, but they did take a long time and they did a lot of testing, and they did actually rework some of the stuff to make it more resilient, which increased the weight, which they were concerned about, vibration once it gets into the Ariane 5 within the fairings, and the vacuum, the change from atmospheric pressure to vacuum. What's the vibration of that, and the temperature shock values? And
Yes.
there are a lot of people working on a lot of things, and they all did a good job as far as I can tell. But think of it this way. If when they go to do imaging, all the images come out with glitches in them, they could never tell that because they have no camera to see the surface of the primary mirrors. So if the primary mirrors are solid, but the gold coating is all scratched up, they will not know that until they actually try and do images, because they can't see it. Remember, there's no camera on the front side. Actually, there's no camera on the front side or the back side. It'll be what it'll be.
Yeah.
I don't quite know where they're going to be doing their first imaging of, but right now it's the way it's pointed. Remember, it's pointed down. The way it's pointed is it's kind of looking towards Ursa Minor. It's in Ophiuchus looking towards Ursa Minor. So maybe they'll pick some galaxy down in that neighborhood to take a look at it. But since I have access to the website that contains all the data, as soon as the data gets loaded onto the website, I will get a notification, because I said, I want to be notified, not just when public data is out there. I want to be notified when any program new data is uploaded. So I should get a notification at the same time as the core science team for that observation. But we shall see.
I think they have a plan for first images.
Oh yeah, yeah. They actually have a plan for not first images, but first sensory light. Because remember, the mirrors have all been pulled away from their launch stations, and they're not actually tilted to converge all the light onto the tertiary mirror at this point. So they have a good portion of a month left to play around with the mirrors before they can do any real science. And the first science will be calibration. And then the next science will be at the discretion of the project manager. So for PR purposes, they may be taking opportunistic pictures. We don't want to spend a lot of rocket fuel. What are we currently pointing at that we can like move a little bit and take a picture of it? Just to have, to feed the hungry masses in the public of, I want to see pretty pictures. So, grab a picture. And then after a period of 6 months, after doing calibration and program managers selected targets, and then you have some, I think it's the best way to describe it is key player observations, where it may be that, parts of the industrial complex that built the Webb wants to check out the capabilities of their instruments that they supplied to the government. So give it about 6 months before we start looking for any real scientific images from principal scientists. But when they get that first public image that they're about to show to the world, I'll get the notification 2 ways. One is I'll get it from their repository system. And the second thing is I'll actually get it from the Space Telescope Science Institute's publicity team, because they want us to do a presentation regarding the content, including the content, before it becomes publicly released, so that we're in kind of the Facebook and YouTube social media channels by the time NASA officially publishes the picture. So
Are we
see.
going to have any first light kind of thing?
I'll be able to see the first captures, but that won't be officially first light. It'll be for sensory calibration.
Yeah,
Everything will
that
be out
would
of
be
focus.
something like that.
But it'll be interesting to see if I get notifications at that level, because anything that winds up in the repository, I should get a notification as it gets loaded to the repository. And that's before the notification I would get for public announcement. So hopefully I won't have that Sophia 1-year waiting period that I
That
had to
was
like,
awful.
if you know how the web works and you put in the request, then you don't get the 1-year waiting period. You can look at the data now. That's not hacking, that's just creative. I didn't violate any security. I didn't, hack any passwords. I just went, oh, I see your URL. I see the parameters. If I just synthesize the same URL, but for a different date and time and, flight operation, I should be able to see what you did. And I could. That's why real IT folks, when they're doing that kind of stuff and making videos accessible to the public, they'll blur out the URL so that people like me can't reverse engineer the URL and hack it.
Not hack it, observe.
Just creative use. I try and convey whatever I find would make it easier to understand things. And if it gets too complicated, people just have to ask. I'm like, well, let me, dig out something that I use to understand it better. Maybe it'll help. So,
That's very good.